Well, so this is the part 2 of the explanation of the video where I asked why is the motor wheel small and the driving wheel big. So before watching the part 2 of the explanation, I would prefer that watch part 1, because in part 1 I had discussed some of the concepts like what is a machine and what is tangential velocity. And the tangential velocity, I mean the concept of tangential velocity, is the most important concept here. So let's start. Well, to understand the purpose of the machine, we have to know its velocity ratio. Now, what is velocity ratio? Of course, from the name you can understand it is a ratio. It is the ratio of the velocity of the point of effort to the velocity of point of load. Its value can be used to determine the purpose of the machine, whether it is a force multiplier or it is a speed multiplier, or is it just for changing the direction of force. Now there is also another quantity called mechanical advantage that can also be used to determine the purpose of the machine. But as we have the quantity of velocity here, then we can just use velocity ratio. Now, if the value of velocity ratio is greater than 1, that means it is a force multiplier. If it is less than 1, then it is a speed multiplier. And if its value is equal to 1, then it is just for changing the direction of force. Now you may ask why? What is the reason behind this? Well, the reason will be answered in the video only. Now, as we are dealing with rotational motion, that means those two wheels, the motor wheel and the driving wheel, both are rotating, right? So as we are dealing with rotational motion, so here for velocity ratio, we will be considering the angular velocity of the two. Now, there's a relation between angular velocity and tangential velocity. That is, tangential velocity equals to angular velocity multiplied by the perpendicular distance between the line of velocity and the axis. Now, in this case, I mean in case of the machine that has been shown in the video, the tangential velocities were along the circumference of the two wheels. So the perpendicular distance from the line of tangential velocity and the axis is actually the radius of the two wheels. So now let's apply this formula for both the wheels of the machine. Now for the motor wheel, Vm, that is tangential velocity of the motor wheel, is equal to omega m, that is angular velocity of the motor wheel, multiplied by the radius of the motor wheel, that is Rm. Similarly, applying this formula for the driving wheel, that is Vd equals to omega d multiplied by Rd. Now we had previously proved that the tangential velocity for both the wheels is same, right? That means Vm equals to Vd. Further solving the equation, we get omega m into Rm equals to omega d into Rd. So we come to the ultimate formula, that is omega m by omega d equals to Rd by Rm. Now the formula omega m by omega d looks familiar, means we have seen it somewhere. Now if you are thinking that omega m by omega d is actually the velocity ratio, then you are exactly right. This formula is the velocity ratio of this system. So we get the velocity ratio as Rd divided by Rm. Now the driving wheel has a bigger radius and the motor wheel has a smaller radius. Therefore, the ratio Rd by Rm is greater than 1. That means omega m by omega d, that is the velocity ratio of the system, is greater than 1. And as I mentioned before, that if the velocity ratio is greater than 1, that means the system is a force multiplier. And that's why we are placing the smaller wheel at the motor wheel and the bigger wheel at the driving wheel. Because being it a force multiplication, we can apply less force at the motor wheel and we can lift a heavier amount of water. It might be slow, but still we can lift a heavier amount of water by a less force. That's why we have this arrangement here. Now you may ask me why. I mean, why a machine having velocity ratio greater than 1 is a force multiplier? Well, for this we need to use the law of conservation of energy. Now I think that everyone knows what is the law of conservation of energy. It is a quite common concept in physics. Now initially the machine has no energy of its own. So as it has no energy of its own, so it can't do any work on the load by itself unless we or any external agent do work on the machine. That means we have to provide some energy to the machine, and the machine will use this energy to do work or give energy to the load. That means suppose there is a machine and I give it 10 joule of energy, or I do a work of 10 joule on the machine, then the machine will also do a work or give a energy of 10 joule to the load. Well, that means the work done by us on the machine is equal to the work done by machine on the load. That means the force applied by us on the machine, that is Fe, multiplied by the displacement of the point of effort, that is dE, equals to the force applied by the machine on the load, that is Fl, multiplied by the displacement of the point of load, that is dL. Now we know that F into D or F into S equals to work done. That's the formula of work or energy, whatever. Now, in the case of the machine we are discussing, we are dealing with rotational motion, right? So we can't use these linear quantities. Rather, we have to take the rotational or angular substitute of those linear quantities. Now the rotational or angular substitute of force is moment of force, that is tau, and the rotational or angular substitute of displacement is angular displacement, that is represented by theta. Now one thing that is common sense, we know that velocity is directly proportional to displacement, right? So that means angular velocity should be also directly proportional to angular displacement. So in this formula, theta L by theta E should be directly proportional to omega L by omega E. Now we had previously proved that omega E by omega L, that was the velocity ratio, that is greater than 1. So omega L by omega E should be less than 1. That also means that tau E by tau L should be also less than 1. That further means tau E is less than tau L, and that proves the point that it is a force multiplier. I mean to say that if tau E is less than tau L, That means the torque we are applying on the motor wheel is less than the torque that the driving wheel it is obtaining. That means with less torque at the motor wheel, we are obtaining a greater torque at the driving wheel. Thus, it is acting as a force multiplier. So you can also see this arrangement in those mountain bikes. There the gear that is attached to the pedal is actually small, and the gear or the back gear or the gear attached to the back wheel is actually big. That means with less torque at the pedal, we can obtain a greater torque at the back wheel. That means it will be a force multiplier, and we can easily climb up the mountain with the mountain bike. And the opposite happens in normal cycle, that you will see that the gear attached to the pedal is large, while the gear attached to the back wheel is small. That means it is acting as a speed multiplier there. Thank you.